Okay, let's go over the functional programming question I did. So here what I have is a question that does first fold fusion, then just kind of properties with that. So the first part we have fold definition of things, right? Pretty straightforward. And then the fold fusion law. And then part A asks us to briefly outline the proof of the fold fusion law with just sufficient details to account for the adequacy of the three conditions. And 2 marks are allocated for this. This is basically a past question that we did before, except it's just less marks. So I guess it means that it's slightly less kind of rigorous. So basically the idea for fold fusion is the following. F of fold GA(x's) is equal to fold HB of x's. So then for the case that x's is equal to bottom, then we have this case, right? On the left-hand side, we have this, which would give f bottom. And then on the right-hand side, the fold of bottom would be bottom. So f of bottom has to equal bottom. So that's the first condition. The second condition is when we put in an empty list, then the left-hand side would be this, which would be f of a, and then by definition of fold, and then the right-hand side would just be b. So f of a is equal to b, and in the third case is x is equal to y of y's. Then we have the following equal, which we could just use definition of fold to extract out g of y, and we would have this. On the right-hand side, we would have this, which we could use the same definition of fold to have hy of fold of the remainder. And the remainder of that, we can use the induction hypothesis, and we can just write it in terms of the left-hand side stuff. And then from there, what we can do is we can put h of y back into the fold, right? And then to put it back into the fold, we would have f of this is just basically equating the two things. So we have the left-hand side and then the right-hand side. So then we can write it in point form, replacing the y with the x, and we would get this. Okay, so yeah, A is done. There's nothing new about A that we haven't known about because this exact same question showed up before. And in part B, we have the standard function map, which is over here. Pretty straightforward definition. Use fold fusion to prove that map F can be written as a fold. So already in the actual thing, I already kind of knew that map of F is equal to this thing. But in reality, you definitely need a proper proof. So I'll go through that. Why is it not loading? Okay, so the actual kind of thing for this would be to use fold fusion on mapf. So what you would do is do mapf dot identity, compose that with identity, right? Identity wouldn't change what it is. And we can rewrite identity on list as fold of cons of an empty list because that doesn't change anything. So then we know that this is fold HB, applying fold fusion with F equals mapf, G equals colons, cons, and the A is equal to empty list. And then we check the three conditions. Map F is strict. Yes, that's true because we have to evaluate F at every point. Map F of the empty list is just equal to B, which is the empty list. And then finally, map F of cons of X AC is H of X of map F ACC. And then we just simplify it a bit. We have the cons, which we just put in properly. And then the right-hand side, well, let's just keep it the same. And then we continue making some progress on the left-hand side by applying F to the first element, X, and then we have the remainder of that part, right? And then we're just going to call our Y's to be map F of ACC. So then we can define our H to be taking in two parameters, X and Y's, and then we're returning F of X, Y's. So map F would just be the fold of H, which is this thing. B was just determined before. Or if we write it in a nicer form, point free form, like the point form, then it would have been just first applying F, then composed of the cons, and then we just have the empty list, right? So yeah, so that's how MapF is written. I think the main idea came from the fact that we know that if we apply something to the identity function can be written as a fold, which then allows us to apply the fold fusion. Part C, we have proved that fold of f of a map G can be written as a fold. Okay, so for this part, what we have is the following. I think I'd rather go over this solution, which looks nicer. So yeah, we're trying to show this, right? Is a fold. So the same idea. If we have this, we just stay with what we have for this part. And then we just showed that map of F can be written as a fold. So we're just going to get the definition that we just wrote into here. Then we apply fold fusion, which would give us F, G, and A are the following. So then we check the three conditions. First check fold FA is strict. Yes, that's true. The second one is B is equal to fold of FA of empty, which is A. And then the third condition is checking FGXY is equal to HX of FY. And now we just plug the following things in and we could get this. And then we can make some progress by simplifying it. And then we would find that H is equal to this thing over here, which we can rewrite simply as taking X and then returning FGX. So hence we can get that fold of this would just be fold of F of G, composed of G of A. So yeah. And moving back, we're back to part D. Prove that map F composed of map G is equal to map F composed of G. So this is just the map law, right? Proving that. To prove this, I guess what I did in the first part was just kind of break it down. But here what I can do is just apply what I already found before, right? Using part B, I know that the map I can replace in terms of just a fold. Then if I write it in the form of a fold, then I can use part C, what I got, right into this. And then I can get, and then this would just be the definition of map of B, right? So then I can just show that it's that case. So it's pretty straightforward. It's just using the part B and C that we got earlier and just working with that. And then for part E, we're given a new definition that compose is equal to fold of compose of identity. And then we're asked to show that composed of map F can be written as a fold. So for this part, what we can just do is um, we can just think of it as just applying C, right? We just know that compose.mapf is a fold. So we can just write a fold of compose identity. This is just the definition of compose, right? Uncomposed of mapf. So then this is just applying C and we would get this. And then if we write this out explicitly, we could have written it out in this way with pattern matching over here. This would just be pattern matching. Or we can just write it in terms of a function like this that takes x and ACC, and then it would return fx of AC composed of ACC. So yeah, that's the idea. And then for part F, we are asked to find conditions under which F compose can be written as the same photo in part E. So this one is just applying fusion and just matching the conditions so that it's the same, right? So we have yeah, we want to show this is the same as part E. So we have this over here. We're going to apply fusion with these parameters. We're going to show that F is strict, which is true. I mean, it has to be true for this to be the same. Then the second condition that has to be the same as B is equal to F of identity. And the third condition that makes it the same would be that F of GXY is equal to HX of FY. And then just showing that, okay, I compose this together and this has to equal. So yeah, these would be the condition, would be that F is strict, and then I'm just applying what the definition for things are, right? B is equal to identity, and then finally F of XY is equal to FX composed of FY for all XY. So yeah, this is just using the fact that I already know these functions from before. And then in part G, we're asked, is compose map equal to map compose? If so, show that. If not, show how it differs. So we're going to show that it's either the same or different. But in terms of just showing the same left-hand side, we can just think of it as the part E with F equals map, right? The form matches exactly. And then the right-hand side would just be part F, with F equals map. And then we would just check that before we just said in the later part that we have these three conditions that must be true for E and F to be the same. So then we just check, okay, map is strict. Yeah. Map identity would be identity. Yes, that's true. And the map of X composed of Y is equal to map X of map Y. And we just proved this identity in part D, so that's true. So since all the three conditions are true, then equality holds. So hence it's the same. And the idea why it's the same is kind of pretty intuitive if we think about it. If we think if we compose map F at 1, F2, F3 all the way to Fn individually versus if we just compose those functions and then map it all together, it would be the same. The order wouldn't matter. So hence it would be equal. But we can show this more rigorously, definitely through using the parts E and F as well as a conclusion in D to show that, okay, yeah, G is true. Okay, this ends off functional programming. I think it's a nice change that I actually got to record this video in the library when there's nobody here today.